and an expert in dynamical systems at Boston University, we worked out what were the possible sources of that oscillation, doing some modeling, all right? And what Nancy helped us sort out was that the most likely candidate for this is the thalamus and the cortex being in an oscillation. All right, so it goes something like this. What we know is if you give propofol, you can shift the rhythms in the cortex down from the beta and gamma rhythms that you see when you're awake down to the 10 hertz. So now the cortex will oscillate at 10 hertz like this. All right, now, the thalamus also has very rich centers with GABAergic sites. And in fact, kind of the master controller around the thalamus is the reticular nucleus of the thalamus. It's a net that sits on the outside like this. All right, now, when the propofol hits the thalamus, the first thing it does is slows down, but it actually stops. Then it probably hyperpolarizes again because it has a hyperpolarizing activating current. And it's well known that once it hyperpolarizes and activates again, it comes back at 10 hertz. Now you've got two major centers in the brain that are highly connected, which can now oscillate at 10 hertz. So it's very likely that that's what you see on the front of the head. So we've actually checked this, and we've actually done the experiment of getting, taking rats, sticking an electrode in the cortex, sticking an electrode in the central thalamus, and actually seeing this oscillation. All right, so that's the first part. Now, for the slow oscillations, we have the good fortune to work with our neurosurgeons and our neurologists in their patients that they bring in for epilepsy surgery. These patients have grid electrodes implanted, right? And it's basically a free anesthesia experiment. They have grids implanted. They come in, they get the grids implanted. They stay in the hospital for 5 to 7 days. I mean, you have these at your hospital. And then they come back to have the resection and have the grids removed, all right? So when they come back, you just monitor the transition into anesthesia. So you not only get field potential and this sort of thing, but you actually get the activity of neurons spiking in the brain as patients transition into unconsciousness. And this is actually the PhD thesis of one of my students, Laura Lewis. And so there are two important things that we learned about these slow oscillations. So here they are. Now look at them here. This is what you would see in the operating room. And this looks just as intense as that, maybe even sort of more intense. But there's an intrinsically different property to it altogether. We saw this in our EEG studies. We see it here in these grid studies. And it's this. On the front of the head, the 10 hertz oscillation is like this. It's very much in sync. This slow oscillation, it's totally discoordinated. It's not in sync at all. It's just like random, basically. All right? That's the first thing. Then, what Laura learned when she said, if I look at how the slow oscillation comes about, right, when do the neurons now spike? All right? Because look, when you're not under the state of anesthesia, neurons can spike whenever they want. Okay? But if you look here, so look at this part here. So this red dot is a slow oscillation coming from that location in the brain. This green dot is a slow oscillation coming from here. Okay? Now, this little histogram is where the neurons that are next to this location in the brain spike. And if you look at what you see here, they spike only at the trough of the slow oscillation. So slow oscillation can spike there, slow oscillation can spike there. But if you look at a location over here, which is about 4 centimeters away, over here at the blue dot there, okay? These guys are out of phase. So slow oscillations which are near each other are in phase like this, right? The neurons can spike in a limited window, so they can perhaps communicate. But now, as soon as you move over here, not that far, 4 centimeters, it's going to be harder to communicate. So it's seemingly like a marker of cortical fragmentation. So you've got two things going on. You've got an alpha oscillation, locking your thalamus and cortex, and you've got your cortex, which is now quite fragmented. Now, so what is this like physically? Why would this give you a state of unconsciousness, like the 10 hertz oscillation? So it's something like this. So you hear my voice now. It's got frequencies in it. Some of them are high, some of them are low, different amplitudes, all right? So if you say, no, Emery, that's cool, that's slick, but what I want you to do is give me the same lecture, but I want you get one frequency, and you got to keep the amplitude the same, all right? So this becomes wah, or if you say, well, okay, I'll give you a band. So it becomes wah, 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 kind of like the adults in the Peanuts, cartoons, right? All right? So you can see that that's not a mode in which you can transmit information, all right? Now, Sujit Vijayan, who was like one of my graduate students and now is a postdoc with Nancy Coppell, spent some time working on this issue of anteriorization. I just wanted to mention it to you because this is one of the kind of the robust neurophysiological phenomena that's been known for years. Tinker and Mitchenfelder pointed this out back in a paper where they studied monkeys, in 1977, all right? And what I've just showed you is just a little bit of additional information on that. It's there. It goes away when you recover consciousness, and it also, the alpha component of it is very, very strongly coherent, all right? And so what Sujit did was he started asking the question, why is it? Why would you have what is it about the brain and anesthetics that, would cause an effect like this? And the key turned out to be the following. There has to be a difference, right? The front and the back can't be the same. Otherwise, you'd have the same sort of dynamics going across the entire head, all right? So the key difference is that there's a subset. There's a subset of cells here, a subset of pyramidal neurons in the occipital cortex that basically have different membrane properties, right? When you apply propofol to them, you essentially arrest those neurons. You basically arrest their ability to enter into the alpha regime. And you actually favor the neurons, the connections going from the thalamus to the frontal cortex of entering into this alpha regime. In other words, so again, look, primary track in vision is lateral geniculate in the thalamus going back to occipital cortex. I mean, it's probably the first neural circuit we learned when we learned neuroscience, all right? So it's clearly thalamus is well connected to the occipital cortex, but the neurons have different properties, all right? So this underlies this, we think, I mean, this is a modeling study, we think this underlies why you see this anteriorization. All right. So we've spent time working on pretty much all of these different stages to try to understand sort of the neurophysiology behind them. And in a second, I'm going to tell you a bit about burst suppression. But I'll just summarize what I've told you at this point. So the alpha oscillation is probably like a hum, a pathological hum. Now, there's a clinical correlation there, too. So our neurologist colleagues have this thing called an alpha coma, all right? An alpha coma is a very bad prognostic sign, right? When patients are in it, it turns out that if they don't get out of it in a few days, the likelihood of recovering is actually pretty bad. It turns out that it's actually primarily frontal. And what I don't know is, because I haven't had a chance to analyze any of these data, is whether or not it's also coherent the same way this is, all right? If that were to be the case, it gives us a little insight into why the alpha coma may be so bad. You have your thalamus and cortical circuits totally locked up, and you can't get out of that regimen, all right? I showed you how the slow oscillations maybe fragment the cortex, and this anteriorization, may contribute to this idea of frontal parietal disconnect. And the first thing I started off with was just showing you clinically how the drugs probably inactivate the sites coming out of the brainstem. Now, but having said that, I think it's important this is a very active area of research. There are a number of investigators who are working on these problems, like doing imaging studies. So Tony Huditz has this really nice review talking about, sort of imaging information that gives us insight into, loss of consciousness. And he makes a very interesting point there that very likely a key component of the cortical effects, maybe the parietal and precuneus areas, sort of here, and the intralaminar nucleus of the thalamus. This is information which has come from imaging studies. And then George Mashour's group and also Gerhard Schneider's group has done work looking at this sort of frontal parietal, disconnection. Gerhard, his paper is actually in anesthesiology. It hasn't come out yet. It's out online. And then recently there was also a publication in anesthesiology on this sort of cortical hypersynchrony. So what I just want to point out is this, what underlies all of this is dynamics, all right? So it's not that things just shut down, it's just that you alter the dynamics in the brain in such a way that it's much more difficult to transmit information. All right, so let me talk about burst suppression. So this is work which has been done primarily by Xunan Qing and Miriam Sunechi. All right, so just to remind you, and so one of the reasons I wanted to work on burst suppression and try to understand it is burst suppression is kind of like a final common pathway. All right? There's several things that lead to burst suppression. So general anesthesia, hypothermia, profound states of coma, and then there are all these sort of things that happen to children. So there's this thing called Ohtahara syndrome, which is a sort of infantile epileptic encephalopathy where the kids are born and the brain, unfortunately, it's not compatible with life. They only live about 18 months or so. But the brain is sort of in this constant state of like burst suppression. And then very often, if you have a post-asphytic event in a child, the seizures will be actually sort of after in a newborn, they actually are in burst suppression. So burst suppression is not just something there's anesthesia. There's some sort of final common pathway there. There's something about what the brain is doing fundamentally that's sort of worth understanding. All right. So I'm just going to show you some insights that we gained first from modeling and then from an experiment. So that's burst suppression, all right? And then Shenung worked out this model of how burst suppression might come about. So I'll just tell you a little factoid. If you look at the burst in the burst suppression, whatever the brain was doing before it entered the burst, that's what it's still doing, okay? So if you're under general anesthesia, and if you can watch this in the operating room, if you watch the transition into burst suppression, if you're in a nice alpha and slow wave pattern, and then you go into burst suppression, then within the burst, you're within an alpha and slow wave pattern. By the same token, if you're seizing, right, the patient's seizing, right, within the burst, right, the person is still basically seizing, right? So there's a preservation of whatever dynamics were there before whatever started the burst suppression began. So what that says is if you have some sort of neurophysiologic process going on, then whatever creates the burst is kind of a meta process. It has to sort of come on top of whatever's occurring, all right? So for obvious reasons, Shenung postulated that this meta process was metabolics, all right? And so he made some predictions about, so if you had burst, that maybe it's related to ATP. And I'm just going to use that kind of very imprecisely, precisely, because there's something about energetics, and we'll just call it ATP for the moment. But one of the things that we do know is that the sodium-potassium pumps of the circuits in the brain depend critically on ATP. So what you could imagine is if you had a drop in your ATP levels or energy levels, you create a leak current, and the leak current could be the suppressions. But the key thing is that his model makes a prediction about the time course of these energetics, all right? That they drop off during the burst, they build back up. When they reach a certain level, you drop off again, all right, after the neuron burst, all right? And there's the time course for the change. So we did an experiment with the help of our colleagues in the imaging center at MGH, in which they measured simultaneously burst suppression and near-infrared spectroscopy. So you could look at the oxy and deoxyhemoglobin levels in the brain at the same time that you're looking at the burst, all right? So if you look here, see the gray things here, they're the burst, right? They're the burst. This red trace here is the time course of oxyhemoglobin. It maps on very nicely to this time course of this energetics process, whatever it is. I mean, you called it ATP, it may not necessarily be ATP, all right? And then if you look at the conductance here, the conductance piece maps on very nicely to the deoxyhemoglobin, all right? So a suggestion that we may have a mechanism or a hint of a mechanism as to what's actually occurring with burst suppression. All right, now, so who cares? All right, so I wanted to, the idea of building a control system for anesthesia has been fascinating me for a few years, and I got even more fascinated by it after I was at this, one of the meetings in Chile. And so we came back and we started working on this problem, but it seemed like such a hard problem. So we decided to start on something which seemingly was easy. So we said, why don't we try to control burst suppression? So why would you want to control burst suppression? Well, when patients are placed in medical coma, it's, they're there for days, they're on a propofol infusion, and someone has to sit there and twiddle the knobs for days to try to keep them in this state of burst suppression. So they have intracranial hypertension, or maybe they're having seizures. So maybe this would be the place to start to develop a therapeutic process. So we began exploring that, all right? So the idea is the following. So you set a target level of burst suppression you want, a fraction of time you want to have suppressed. And if you have a model for your system, like here, then that would suggest a target propofol level, in this case, that you want. That could control a syringe, which would be injected into a rat volunteer, and then you measure the EEG, you process it in real time, you figure out if you're actually at that estimated level, and you adjust your process accordingly, all right? So here's real EEG coming out of one of these rats. It gets thresholded, and then it gets converted to these binary events. And then one of the things that my group has worked on for years is these algorithms to actually analyze what neurons do. And neurons are basically binary events. So dynamic algorithms, which could take neural signals like these and process them in real time, is something that we were pretty practiced at, all right? So let me just show you this, all right? Oh, and just before I say that, though, so this idea of this burst suppression probability, it's just like the BSR, the suppression ratio, that's used in like a lot of the algorithms on some of the brain monitors, all right? It's just the fraction of time that the patient is in a state of suppression, all right? So here's this little video. This is that Miriam made just to illustrate this. All right, so the first thing we do is you're just going to set a level. All right, so the green line is the level that's set, and all this is happening in real time. And then the white line is going to be what the controller is supposed to track, all right? There's no audio with this. So now we'll change the level. Change it again. And you can see down here, this is the infusion rate, how the infusion rate has to change in order to maintain the level of control, all right? So that's obviously sped up. That's about, an hour. The video is about a minute, all right? So it gives you some sense. So this is just, this is just some of the, illustrations from that. This is the one I just showed you here, where, you say go up, go up. Here is, go down, then go back up. So it's a very tractable problem. It's not the algorithm in here is this is not a standard PI controller. This is a stochastic controller, which is using both LQR and also model predictive control. But the problem is very tractable, and it's probably something which could be done fairly readily once you had sort of the right signals. See, the reason I started with burst suppression is burst suppression is obvious. Even I can see it. It's burst suppression, right? So as we had better insights into some of the other signals, maybe something similar could be done with other states of anesthesia. So that's what I just said, all right? So maybe you could use this. And if you think about it, right, the way it's done now, someone is in burst, you're going to use burst suppression to treat someone who's in a medical coma. It's just like saying, okay, I'm going to fly the plane for 5 days, and what I want you to do is keep your hands on you're not going to use an autopilot, right? We're going to keep your hands on the stick the whole time, right? It makes no sense, right? It's probably even more compelling time to have a controller than, in the operating room, all right? So the final thing I just want to share with you is just some work which is being done by Ken Salt, who's been looking at this idea of maybe having us come out of anesthesia. We reverse everything. Manfred was talking about reversing neuromuscular blockade. We reverse heparin. But maybe we should bring the brain out of anesthesia actively. Maybe part of the reasons that we have cognitive dysfunction or delirium or persistent effects of the anesthetics is we've turned the brain off profoundly. We've left it there. Arguably, these are pathologic states. They're not natural states. Maybe we should just flip the switch and bring it back on. All right, so Ken's worked on that a fair amount. And I'm just going to illustrate one particular case where he's done this. So again, this is one of our willing rat volunteers. And so he's stretched out there, breathing isoflurane. And he has an IV in his tail vein. And so he's been there for about 20 minutes or so. And Ken's going to give him just a saline injection, basically to show you that if you inject saline, nothing happens. All right, so let a little time go by. Let a little time go by, and now Ken's going to inject